We're ready. Mr. Morillo, you're on. Welcome.
Fantastic. Not to change the topic and completely pivot on otherworldly experiences now, but we're going to talk about Mars today.
All right, good deal.
And again, thank you guys for having me. I want to talk a little bit about my story as well, because it's going to probably be very similar to where you guys are at today. And my background is, I'm an immigrant. I'm entirely an immigrant. And I'll talk about that in a bit. And it's been quite the journey to get where I am today. And I've had a lot of technical experiences and a lot of help bringing me up here. And I like paying it forward, which is why I'm sitting here with you guys today. First and foremost, let me see. You guys can see my slides well at this point, right?
Yes.
I'm not just speaking into them. Okay, good. I don't.
Elio.
Hey, Alejandro. Thanks
How
for
you
the
doing?
invite. Good.
Sorry for
Good.
coming in late.
It's all good. We're starting just now.
Okay.
So first and foremost, I always like to highlight my mom. Right? Without my mom's determination and her sacrifices, I would not be anywhere where I am today. And if you're wondering who it is in this picture, it's the one that fiercely looking at the camera, with the suit. She was a principal at a school in Ecuador, and that's where this picture was taken, in Guayaquil, which is where I was born. And lots of things happened in the 90s that ultimately led my mom to decide that it was best for us to go to New York. In New York, we had some family already that had moved over the years, including some of my aunts, some of my uncles. New York City, they still live there. They live in between Brooklyn and Queens. Families spread all over the city. And my mom decided, you know what, it's probably best for us to go there. And despite her not knowing any English and having had basically a 20 plus year long career as a teacher, principal, she was a professor, all of this, both in the public and private sector, she gave it all up to move to New York City, where she didn't know the language. I didn't know the language. I was 4 years old when she decided to move. And fortunately, we had the family to support us there. My mom had to pick up cleaning jobs. She had to put her pride aside. She worked at JFK as, packaging food, and all of that to make ends meet so that I could have food to eat. I could continue my education. And ever since I was a little kid, having my mom as a teacher, I had a constant reminder that education is, what pushes us forward. And no matter what you do, always stay learning. It's important, and it'll help you out throughout your lives at any point in time. And, we were there for about 2 years, and for circumstances, it's a completely different story. My older brother, who's 15 years older than I am, who's also in New York at the time, he marries a Puerto Rican. So he moves to Puerto Rico. And my mom sees that as, an opportunity to move to Puerto Rico, which is still part of the United States, the colony of the United States. And being there, she could go back and teach and continue her profession. And that was the case. We moved to Puerto Rico. My mom immediately found a job as a teacher, having all the experience she had. She hustled through to get through private schools and ultimately ended up getting her license to teach in Puerto Rico, and basically accredit all of her education after all the years. And while we were there, I spent my childhood in Puerto Rico. So I have this dual Hispanic culture on my back, which, at home it was Ecuadorian all over the place. I mean, I was living in Puerto Rico. I grew up in Caguas, Puerto Rico. Like, that's my Spanish is super mixed. And while we were there in 2000s, or in early 2000s and towards 2006, that's where the economy in Puerto Rico really starts spiraling out of control. And my mom started noticing the patterns because she had lived through this in Ecuador. And the first things to get cut are typically the teachers. That's unfortunately how things just work in our governments. And she was worried that was going to happen. So 2006 comes around. My brother also moves to Florida. Many people from Puerto Rico moved to Florida. And my mom and I, stayed there for a few months, figuring out what we were going to do next. And my mom thought it was important for us to move back to New York. At this point in time, I was in the middle of middle school, so I was about to go to high school. But I was very conscious of my friends, my relationships in Puerto Rico, with friends and people I considered family. It was way tougher for me because I was growing up. I had all my connections there. But I had to trust my mom. I had to trust her judgment and what she thought was going to be best for me. And moving to New York, it was a complete culture shock. I moved there in the middle of 8th grade, and if you guys have heard, New York City is one of the most segregated public school systems in the country, and I lived through that unknowingly. I only learned recently what it really meant to be in that, thanks to the New York Times article on standardized testing that came out in the New York Times last year. Where some people are exposed to this magical test that it gets them admission to top high schools. I had no idea that was a thing. And to give you kind of a picture into the hurdles I experienced and my mom experiences when I moved to New York in that middle of the 8th grade, I had what the counselor at the time considered way too good of grades. So he deflated my grades because according to him, no one would believe that my grades would be that good as, this kid that just showed up from Puerto Rico and all of a sudden just handles everything. I didn't even know what that meant, but that carries a lot of weight. And that was probably the big first hurdle I experienced, and I didn't know any better. So my mom, when she heard about that, not knowing English, she went to the district, she fought, she brought it up against a bunch of people, and ultimately they fixed all of that in the documentation, and I was able to go into a pretty good high school. And I like to show this picture because a lot of these people, this is, I think, sophomore year of high school, I'm still in touch with today. I think something that's very important, and many of you may have already realized this, surround yourself by people that will support you, people that are ambitious, people that will push you to be better. And similarly, support them. I think that's very important, and pay it forward, because we're all at the end of the day, this big community, and with these friends in particular, we all went to different colleges, but we all pushed each other to be our best. And to this day, we stay in touch. Most of the people in the picture, making sure, keeping tabs on each other. We see each other at least once a year. I think that's very important, very powerful. And, New York City's rough, being low income. As you guys know, rent there is expensive. My mom made it work, working 2 jobs. She still remained, when we went back there, once again, she gave up her profession to clean offices, to be a home attendant and take care of elderly folks. And sometimes I would go into office and help her. It was the reality of things. But it was always very clear that I had to do well in school. So I did that. I was one of the top students in the class, along with a few of the folks in the picture here. And, we pushed each other and supported each other. And I was fortunate enough, just like you guys have, Mr. Alonso, I had an awesome chemistry teacher that, found opportunities for us. And in high school, he partnered with a professor at NYU that, gave us data from the Spitzer telescope, which is an infrared, has an infrared, it analyzes the infrared spectrum of images across different galaxies. And we were characterizing black holes. And looking back at that, I didn't realize the magnitude of that. In high school, I was doing research in astrophysics, looking at black holes. And then not only that, he found the opportunity for us so that we could go present this data at the American Astronomical Society conference back in 2010, where, it was my best friend and I at the time. These 2 high school students were there with, Bill Nye, the different astronomers of the world, the different institutes across the country. I didn't know what that meant. We went to Washington, D.C. on a train and just brought our poster along. And then, looking back at that, it is incredible what teachers do for us. And I'm always going to be eternally grateful for that level of support. Following that experience, one of the summers as a high school student, you guys have your first robotics, something I wish I would have had back then. So definitely take advantage of this. my very first exposure to robotics was at the Cooper Union, a local college in New York City, one of the top colleges in New York City. There was a summer program where we got to design and build a pretty basic robot at the time, but that was the first time I had exposure to CAD, first time I delved into some C programming and had a ton of fun. And that's when I realized I want to work in electromechanics. Now, at the time, here I am, about 2008, 2010 timeframe. That's when Iron Man was coming out. So I had the inspiration of Tony Stark the entire time while I was in high school. I wanted to be Tony Stark. I still want to be Tony Stark because, he's Tony Stark. And, working on the different aircraft and the space, the spacecraft that the United States is well known for, it's part of that American dream that is very much a reality for many of us. And working hard to be able to achieve and working on a lot of these technologies. And so far, I can tell you guys that it has been the case for me. And, similar to you guys and many of you right now, I went through this drill. I had to figure out a lot of this on my own because my mom didn't know really the application process in the United States, how complex it is, taking NDP exams, getting mentoring, taking the SAT, doing the SAT2s, FAFSA, the Common App, all this stuff, all the grind. You have to do it, and you have to get people to review all this material because it's really important. Because I cannot stress enough how life-changing will be for many of you to go off to university, or even community college and then university, whatever it is you do. It will change your lives and for the better. It's incredible the kind of experiences and people you meet along the process. And I didn't necessarily understand that. I appreciate it now because I lived through it. But it's critical, and I like to talk about that because, one thing led to another. And I originally thought I was going to go to Carnegie Mellon University to be an electrical engineer, and then I was convinced by the University of Michigan to go there. And I had even a presidential scholarship for University of Virginia. But Michigan convinced me because they were one of the schools that flew me out. They had messed up my mailing address, so I didn't get a lot of materials in time. There was a summer program. There was a transition program between high school and freshman year that, I understood. I was coming from a public school from New York City. I knew I was not going to be top of the class at Michigan. I knew I was going to be a complete, I was going to be competitive. I was going to go after what I wanted, but I was very well aware that there were kids out there that came with better preparation, had way more money than I ever did. And I wanted that toe dip into the college experience. And that's what this program offered for me. I was in Ann Arbor for 6 weeks in the summer, and we did a 22 credit hour simulation. So we took physics, programming, math, according to our respective levels, and did some what was it called? I forget the name, but it was a class where we basically showed up and we talked about our stories with each other. Because as technical as you all want to be, at the end of the day, it's critical that you learn how to manage your very human relationships and your networking abilities. I cannot stress enough, even if you decide to be engineers, how important it is for all of you to learn how to communicate with each other. That being technically, as well as your soft skills, learning how to convince people at the end of the day to do your bidding, right? But you have to be tactful about it. There's all kinds of courses and methods for that. Something to be on the lookout for as you move forward. Now, when I went to the University of Michigan, plenty of experiences there, from a technical perspective. I interned at GE Aviation working on Super Hornet engines. I worked at SpaceX. I worked on the Crew Dragon vehicle. I went to Boeing and did some missile design work as well as some Black Project work. And as a master's student, which everybody here, if you don't already plan on obtaining a graduate degree, put that on your list because you should. And also just always remember never to pay for it because there's many people trying to throw money at you. So you go get that graduate degree. No matter what it is you want to do, there is money and there is funding for it.
Sorry to cut you off there. Hi, Elio.
Yeah.
I just wanted to emphasize on that because I always push our students or our team to at least get a master's degree because I think they'll go really far going that and they'll benefit a lot. They won't realize it at that moment, but after 5-10 years, they'll know that, oh yeah, I made a great decision.
Exactly. And it's sometimes okay to take a break between your undergrad and your master's degree. I've seen plenty of people do that. Just try to be mindful um, how that fits into your own personal story, whatever your personal circumstances is. Go to one school versus another. I did both my undergraduate degree in mechanical engineering with a minor in electrical engineering and then I did my master's in spacecraft design at the University of Michigan. But that just worked out for me for many reasons. Fully funded grad program through the University of Michigan. I'm the kind of person I don't like people telling me what to do, so I didn't look for JPL to pay for my master's, but that is an option where companies will pay for your master's, but then that typically means you have to work for said company for X amount of time. I found my own fellowships, just like many of you are probably looking for scholarships for school. Highly encourage you to spend the time writing good essays, looking for scholarships, looking for money. Keep in mind that many times you'll spend an hour or two and get $1,000 scholarship, $2,000 scholarship, whatever it is, but you're making $1,000 an hour, something like that, right? So be mindful of that and go get that money. There's a lot of money that people want to throw your way. One thing for sure that I am very proud of to this day is that not once did I pull an all-nighter as an undergrad. Not once did I pull an all-nighter as a grad student. And I had a ton of fun and my GPA was fantastic. This picture is evidence of that. I didn't know anything about football. You go to University of Michigan, football is just thrown in your face from day one, and then you learn about the history and the rivalries and all that culture. And you know what? I partook in that. I dressed up as one of these. I'm the guy in the yellow suit, one of these flailing arm guys. Having a ton of fun, going to tailgates. Teacher, don't listen to this, but I partied. I had a great time. I did very well in school. And that's part of the college experience and go live that, right? You're going to go there to get your education. You're also going to go there to network, meet lifelong friends, and, travel the world even. That's something I never had an opportunity to do. And I traveled to many places. While I was in college, I even went to the World Cup in Brazil when that happened. And that's because of one of my internships. I made money. So I was like, I'm going to go spend this money and go to Brazil and hang out with a ton of people that flew in. Things like this that you don't realize are so impactful that come with the university experience, I highly encourage you to consider. All right. So once again, all of this you'll figure out. You are going to have your own very unique experience. And remember to have fun and slow down if you need to. It's okay. You're only competing against yourself. You're not competing against your classmate anymore. Forget that. That disappears the moment you step out of university. Yes, there's a grading curve. Yes, grades matter to a certain degree. But always be mindful that you need to understand how the system works for you and, shape yourself accordingly because, if you need to take a little longer than the typical 4 years, it's okay. It's okay to take 4.5. It's okay to take 5. It's okay to take 6 years. Life changes. Life comes at you fast. And you have to adapt. It's kind of the reality. I will admit, in a sense, being an immigrant prepared me for that. And life comes at me fast all the time. And I've been used to just being able to adapt. And that may be very challenging for many of you. And that's okay. Always just, again, back to the networking, building that family on campus, building that family with each other and those friendships. Use those support networks to make sure you're doing okay at the end of the day. All right. So just to recap, right, here's kind of where I've been. I was born in Ecuador, moved to New York, went to Puerto Rico, from Puerto Rico went back to New York, and from New York to Ann Arbor, now in LA. What comes next? I have no idea, right? You would have asked me in high school what I wanted to do is work on an extraordinary space mission that was going to, contribute to our understanding of our position in the universe. That's exactly what I'm doing. What I want to do from here, TBD, separate discussion. But, again, I'm being adaptable in many ways. And just like, you guys have all been thrown off by the pandemic, I do want to have you guys understand that you're living through something many of us have never lived. You guys are going to receive a very different world than what we received when we left college, when we left high school. So we're going to learn a lot from you and the challenges that you are currently going through. So the fact that you guys still have a FIRST robotics team working and functioning and have, your support from your teachers, it's fantastic. Recognize that it's very unique and continue taking advantage of that. Let me talk a little bit about JPL now. Enough about me. And I'm sure you guys have heard a little bit about the lab. The lab is in Pasadena, California. It's this awesome location. It's in Los Angeles. We have the snow-top mountains nearby. We have the beach 40 minutes away. I'm going to go surfing tomorrow with a ton of friends. It's the kind of really cool environment that we have going on here in LA. And the cool thing about JPL, this little building you guys see, I don't know if you guys can see my cursor. Can you guys see my cursor? Not quite sure. Yeah, so if you see my cursor, that building right there is headquarters. So that building right behind it is our mission control. And that's a combination across several buildings, but this particular area I like to highlight because we lovingly refer to it as the center of the universe. Why do you think we call it the center of the universe? And that's because, across the globe, we have the Deep Space Network. We have these big antennas, one here in California, one in Spain, one in Australia. And what that allows us to do is always have visibility of the solar system at all directions from planet Earth. Now, all that data ultimately comes to this building. And which is why, we have all of our assets flying through space in our solar system, flying by Jupiter, flying by Saturn. We have some interstellar spacecraft, the Voyagers, that were launched in the 70s and are still flying. All of the data, coming in and out are being filtered through here prior to being spread out to the different scientific communities across the planet. So it's an awesome place. And typically it's open and you can walk in to the viewing gallery and see what's going on. And obviously many of our high profile events will happen from here, and looking forward to the Mars 2020 landing, which is coming up. And I'll talk about that in a moment. In particular, today I'm here to talk about Mars because that's what I do. I work on Mars. The past 4 years I've been at JPL. This is where my focus has been. And as many of you may know, it sounds like a few of you watched The Martian and know Matt Damon's story here. Mars presents itself to us as a very reachable planet to bring along and extend ourselves as humans, and ultimately colonize that planet at some point in time. Now, to get there, we first of all have all kinds of scientific endeavors to have to understand the planet itself and the resources on the surface, and ultimately determine how would we be able to survive on the planet. Now, the missions and NASA has been on the surface since the 70s, and over time we've developed the knowledge, right? Gravity on Mars is about a third that it is here on Earth. The atmosphere is very thin, which presents its challenges and also provides its benefits in certain ways. It's a percent compared to the atmosphere here on Earth, and it's primarily made out of carbon dioxide. Obviously here on Earth, it's nitrogen and oxygen, but this presents its challenges while also at the same time gives us a way to take advantage of it. Now, Mars is also pretty cold, and it does have seasons. We have confirmed that Mars experiences seasons. It's tilted in a way that is very similar to that of Earth. The big difference, I think, is that one lap around the sun for Mars is basically 2 years for Earth. So that kind of presents its challenges, and the Martian day is slightly longer than the Earth day. So we distinctively call, as some of you know, a Martian day, we refer to them as sols. That way we can communicate in our local lingo and how we operate our spacecraft and vehicles on Mars and around Mars. So like I briefly mentioned, we've been on Mars since the 70s. And the continuous presence there has allowed us to slowly but surely build different blocks of knowledge to ultimately try and answer whether or not there's life on the planet, or was there life, or were there ingredients to support life at some point in time. Now, we have 3 different vehicles for now, and I'll specify 3 for now because there's a 4th one coming up. We have three types of vehicles that we send to Mars. Number one, landers, right? These are platforms that typically land on a specific location and don't move. They do not have wheels. The difference with that, of course, are rovers, which are very similar to the robots you're used to seeing, which allow us to bring scientific laboratories to explore the surface of Mars that have been predetermined in certain locations, and kind of explore, right? There are geologists on Mars. And of course, we have our orbiters, which are the assets we use to take images of the surface, as well as communicate with the assets on the ground and relay that data back to Earth. So I'll focus a little bit on the rovers here, because that's what I work on and what I want to get to. The first time we sent a rover to Mars was, late 90s. It was Pathfinder, it was Sojourner. This vehicle was kind of a demonstration. It was a tech demo, a technology demonstration to help us understand whether or not we could operate a vehicle on the surface of Mars, a rover on the surface of Mars in particular. And what that did is, we figured out, we figured out, first of all, how do we land such a vehicle? How do we do the entry, descent, and landing? Which, again, it's something very difficult to do on Mars, because we have such a thin atmosphere. We can take so much advantage of the gravity there, but when we're entering the atmosphere of Mars, we're ranging, our speeds are along the lines of 12,000 miles per hour. So we have to slow down from that speed to a safe 0 miles per hour on the surface within a period of time. And we learned how to do that with Sojourner. We then reused some of that architecture with the Mars exploration rovers, which are Spirit and Opportunity, which some of you may be familiar with. Mars exploration rover was designed to last 90 sols on the surface of Mars. Both vehicles way overdid their life expectancy, where Spirit lasted, I think, about 4 years, and Opportunity was roving around up until 2018. Which speaks to the level of engineering of the spacecraft that NASA is responsible for, and JPL in particular. The beauty, and I think the major contribution of the Mars exploration rovers, is that they helped us understand whether or not there's water, or there was evidence of water on the surface of Mars. So how do we do that? So if you today go walk to a river, you go walk to a lake, you pick up a rock and you split it in half, more than likely, you look at this rock and you'll notice that it has layers. It has different layers that were built there over millions or thousands of years. That happens in the presence of water. As water flows, material gets deposited on top of each other, and over time, pressure builds up, and that's how you get these sedimentary rocks. Well, using that knowledge we've built here on Earth, we took a look at several locations on Mars where we suspected, that water once flowed. And we confirmed there are sedimentary rocks on the surface of Mars, which ultimately concludes, yes, there is, there was water at some point. And we have also found that there's ice on Mars. And there have been some papers recently published about flow of water. Has to do with high salinity liquid, but that stuff, I guess I'll let you guys Google. But that has been a combination of data between several of the assets. But with Mars, with the Mars exploration rovers, that's kind of the major contribution in the scientific realm. Then, of course, came Curiosity, big rover that landed on Mars while I was in college. And one thing I have to recommend to everyone here is go look up the 7 Minutes of Terror on YouTube. If you want to get pumped up, that video explains the entry, descent, and landing process for Curiosity. And it's fantastic. It is miracle upon miracle that has to go right. Lots and lots of engineering goes into the design as well as the testing, which is what I do, to make sure that we have the best chance and reduce risk as best as we can so that we can land safely on the surface of Mars. So Curiosity then ultimately concludes, or helps us conclude, that there is organic material on the surface of Mars. Now, organic material can be both a result of metabolic processes that happen in biological processes, or also geological processes that happen over many, many years. That's where Perseverance is going to come in. Perseverance now is a bit more complex, has a completely different suite of instruments that'll allow us to get to those questions, and I'll talk about them in a bit, of getting more into the deep answer, the deep question of whether or not there's evidence of biosignatures on the surface of Mars. Of course, I also like to highlight the InSight lander, which landed in 2018. And that vehicle, I like to think of, it's trying to listen to the heartbeat of Mars. It has a seismometer, and it picked up that there is in fact still some tectonic activity on Mars, and there's Marsquakes. You know, we have earthquakes here, and on Mars we have Marsquakes. And along with that, if you have been following along on social media, we are currently still deploying the MOLE, which is an instrument that's going to allow us to characterize the thermal characteristics of the Martian surface and help us extrapolate data to fit models that then tell us how, what's the core look like on Mars, something we don't have a thorough understanding of yet. Again, I like to show this picture to kind of show you guys the scale of these robots, the rovers in particular. See a little Sojourner back, down in the bottom left. It's tiny, about the size of a microwave. And kind of the scaling of the price range of what this costs. And that includes the actual design, development, and operations, as well as the Mars exploration rovers, which were 2 rovers, about the size of a golf cart. And then, of course, you have MSL, the Curiosity rover, which really does have the size of about a Mini Cooper. So just another cool picture I like to show, alongside the folks that, these engineers that are hanging out in the Mars yard, which I have a more recent picture that I'm going to show you guys because that's where I spend a lot of time nowadays. With that, we get to Mars 2020. Mars 2020 is an international collaboration, as all of these missions mostly are, and we're going to continue to do remote science as well as contact science, 2 very distinct approaches to understanding the context of where we're going to land, which is the Jezero crater. You can think of Jezero crater to be somewhat similar to the Mississippi Delta, where water flows into a massive body of water, and what we find in Jezero crater is kind of like the remnants of such a body of water that was there billions of years ago. And along with that, where there's, where water flows, typically, here on Earth we find life. So the hope is let's go find and understand what's there. Will we find evidence, biosignatures, fossilized, alive? We don't know. We'll see. And that's the cool thing about Mars 2020. We have 4 primary objectives. Number 1 is to continue these geological studies, continue understanding the environment there. Number 2, figure out traces of, see if we can find biosignatures to understand what's there. And number 3, also, there's a really cool instrument called MOXIE. Like I mentioned earlier, the primary, component of the atmosphere is carbon dioxide. What MOXIE is going to help us characterize is how can we use that Martian carbon dioxide to convert it into usable oxygen, which is obviously a very critical piece of technology for our eventual human presence on the surface of Mars, because we need oxygen to survive, as many of you pointed out, as well as to generate rocket fuel, to have that ability to come back home eventually. And along with that, if we find something interesting enough, we have an entire robotic system, arguably the most complex robotic system that has ever flown to space, the sample caching system. Identify samples that, that are interesting enough that we can encapsulate them, put them in a sample tube so that an eventual mission returns the samples to Earth for more in-depth analysis. Because of course, there's only so much the instruments on board can do. But if we bring these samples back to Earth, we can take them to all kinds of science laboratories all across the nation and all across the world so that the scientific community can take a deeper look. And with that being said, there are plenty of planetary protection guidelines that we follow to make sure, if we do find something and we accidentally bring, some kind of remnant bacteria, remnant virus, that we don't have that Andromeda strain that our Earth biodefenses wouldn't be able to handle, right? There's all these things are very realistic scenarios that we consider when we've designed all of these systems. So I've been particularly involved with the mechanism testing of a lot of on the rover here, as well as some of the uh, basically all of the cameras. Another fun fact about this mission, there are 23 cameras we're bringing that are going to allow us to record images and video ranging from the actual entry, descent, and landing process, something that we have never done. You can think of them literally as GoPros that we're bringing along with us. They're not GoPros. GoPros missed out on being our preferred cameras. They declined for whatever reason. I don't know what kind of marketing team they have, but they declined to be our cameras. But we are bringing GoPro-like cameras to be able to record the entry, descent, and landing process, as well as microphones. We've never actually actively listened to what that sounds like. And, you know, as these rovers, they're an extension of ourselves. So how awesome is it going to be that we're going to not only be able to visually see what's on the surface of Mars, but we're also going to be able to listen to what that event is like. And then, of course, on the surface of Mars, continue to hear all the winds and the environments around us, which I think is going to be just an awesome feat of engineering. Of course, plenty of details and all the kind of scientific capabilities these instruments have. I do invite all of you to look that up online, because we can just have an entire discussion on what each of these do. But at the end of the day, they're going to be used for those objectives that I talked about. Something in addition that I love to talk about, some people are not aware, because I personally think NASA could do a better job at marketing this. We're bringing a helicopter with us. We're bringing this drone. Just a little more than 100 years ago here on Earth, we were learning how to fly on Earth. And now we're at a point in history where we're going to fly a vehicle on another planet. It is a first for many reasons. And just like Sojourner was a technical demonstration vehicle for rovers, this helicopter is a technical demonstration vehicle so that eventually one day, instead of sending rovers, we could potentially send swarms of helicopters. Astronauts that are eventually going to be on the surface would bring swarms with them to serve as scouts and as scientific instruments. Because having an aerial capability is a very different capability than just having rovers, right? Of course, it has its challenges because it is small. It's very, you know, it's packaged in a very special way. But the battery has to last enough to provide 90-second flights, as well as keep a heater overnight on so that the battery does not freeze up. So all kinds of trades we have to consider in the harsh Martian environment. But very much looking forward to the execution and the deployment of this vehicle, because I've been working on a lot of the testing for this on the system side for quite some time. So that being said, you know, my day-to-day, I'm very much active. You know, I like providing outreach. I like coming to groups like this and talking about this awesome technology. I'm involved in the Society of Hispanic Professional Engineers. It's something I've been involved in since college. Something I invite all of you to look into. Similarly, there are, you know, other sibling organizations out in STEM, the LGBTQ community, NESB, ACES. There's a ton that will, for many of you, create a family at the respective campuses that you go to, as well as provide all kinds of avenues for mentorship and opportunities for you to network and get opportunities to do things like this. Work at JPL, for example. I love this picture. A few weeks ago, you know, I said early on that I was very proud of the fact that I never had to pull an all-nighter. In college, I had to pull an all-nighter here at work because we encountered a problem, and I had to stay up all night in the lab trying to debug it, and that was quite the experience. And I like to have fun with what I do. So fortunately, a lot of this stuff is public knowledge, so I just post it on Instagram. So if you guys would like to see more funny pictures, I mean, feel free to follow. There's a lot of really cool pictures I like to put on there. And my day-to-day, you know, I'm in there with the hardware. I'm in there building dioramas of the Martian surface, taking, you know, the robotic arm, putting it through scenarios very similar to what we would do on the surface of Mars. And similarly with the different instruments, the different mechanisms, so that we're prepared for once we get to the surface, we fully know how to use the vehicle. And not only that, but we use our system test bed so that if we run into problems in the real mission, you know, we can't send a mechanic. We're not there yet. We're going to have to figure out how to replicate the issues here with our system test bed and come up with solutions so that then we hopefully fix problems through software, which many times, more often than not, we can do that. On the right is an image of what I lovingly call the crashed version of the helicopter. It's a desktop version of the helicopter, mostly commercially off the shelf, parts that we've put together to replicate, communication with the helicopter, with the system testbed. And again, the system testbed you can think of as the Earth version of the real vehicle. It's engineering hardware that is never going to fly, but functions just like the vehicle. And that allows us to kind of go to town with our testing. Things we would never want to do with our flight vehicle, we do with our engineering models, just to stress test and understand all those interactions between hardware and software that are so important to characterize prior to us fully commissioning the usage on the surface of Mars. So, that's my story in a gist, and my technical story in a gist. Really looking forward to February 2021 when we land on the surface of Mars. It's going to be exciting. Obviously, all of you will have access to all the live streams, and I'll show you guys this picture of what's next, right? So this is a cool architecture. Nothing is set in stone for now, but it's an example of what we would potentially need to do to bring back those samples I'm talking about, those very interesting sample tubes that we'll collect up to 30-something samples. We'll have to send some kind of fetch vehicle from Earth to do the whole entry, descent, and landing. But now, for the first time in history, we'd have to return those samples, take Perseverance, give those samples to the whatever fetch vehicle, and then launch that from the surface of Mars and ultimately bring it back to Earth. That's something that we've never done. So very challenging. And of course, in the timeline you guys are in, this is stuff you'll be able to get involved in if you want to. By the time you're in college, by the time you're graduating college, Mars sample return is probably going to be a very real project. So be on the lookout if that's something you're interested in. I like to finish off this discussion with a picture of Earth from Curiosity. I think I like to highlight the fact that in this picture, it's very clear that everything we know and love lives in that little pixel, on that little dot. And ultimately, right, someone's going to be on the surface of Mars looking up, and we'll see Earth from the surface of Mars. And very likely it could be any of you. I say nose goes. There's a reason I work on robots to do it for me. I am not nearly courageous enough to go on that 7-month adventure in a space capsule, and risking not being able to come back home. But the first group of humans that goes to Mars are going to be amongst the most brave people that have ever lived. And something to also be aware of is looking up and looking at pictures like this. It helps us, at least me personally, understand how unique Earth is, and how special it is, and how important it is that we take care of it, and ultimately how special, how much we have to take care of each other as well. So with that being said, I'll give you guys a few minutes of questions. Hopefully you guys learned something new, and if not, add me on Instagram and follow up there as well. I'm totally cool with it, because I really don't have all that much time. I'll give you guys a few minutes to ask me some questions.
Well, first I want to thank you, Elio, for presenting this to our students and our team, actually, a robotics team, and talking about Mars, because Mars is very much like Earth. All the characteristics are there, but there's no trees, nothing, just rocks and sand. But those rocks and sand are very, very similar to Earth, and canyons and so forth, like the Grand Canyon. You see a lot of characteristics.
Exactly.
Here on
Mars. And we do take our mobility system and test it out in the desert here nearby. And there's a really good question that's being asked here about how do we simulate lower gravity. What we do is actually we have another rover. So these are things you have to consider. Like, what do you actually want to test under lower gravity loads? 2 examples I'll give you real quick. Number 1, the helicopter, right? The helicopter is designed to fly on Mars. How do we simulate Mars gravity? Really easy, actually. You use a pulley system. And as this, you throw in the helicopter in a low pressure environment where we pump down the pressure to be very similar to Mars. And then you use a pulley system to assist it enough so that the vehicle thinks it's undergoing Martian gravity. So That's how we were able to fine tune the flight controller to help us fly on Mars. Similarly, this rover that you guys see that I'm standing next to, this is a mobility rover that is designed obviously with all the instruments and all the loads, and it's a heavy vehicle. This would be way heavier. It doesn't simulate the dynamics, is what I'll get to. It doesn't simulate the dynamics that the wheels experience, for example. So we have a separate vehicle for that. That is, we lovingly call it the Scarecrow vehicle. The Scarecrow vehicle is, you can think of a scaled down version of the rover that only has the mobility system and some electronics that then allow us to simulate the loading on the wheels as if we were experiencing them on Mars. And that's how we kind of have to get around, and you have to get really creative about how you approach the testing program. Hopefully that answers your question. Is it possible for us to terraform Mars? That is going to be an answer that's going to be answered across thousands of years. Is it possible? Sure. How do we do it? There's plenty of ways. There's plenty of papers out there. It's going to happen. It's going to take a long time, though. Let's see here. What were some of your challenges of using a drone? It's the first time we're going to do it. We don't fully understand how it's going to go. It's going to be flown up to 5 times. The limitations of the vehicle is that in order for us to be able to fly it safely, we've agreed that we're going to fly it about 1 kilometer away from the rover, but that also limits the way we communicate with it. So we're going to fly it up to 5 times, see if it works. If it doesn't, there are different flight patterns that we're going to be testing. And once we're done, we're very likely going to have to leave it behind so that the rover itself can continue on to its surface missions, as it has to complete certain objectives by the first 2 years during its main mission, as we've agreed with the funding and the proposals. Hopefully that answers your question. Thin atmosphere. Well, we spin the propellers way faster than we would on Earth. Fun fact, they're made out of fiberglass, so they would shatter if you were to spin them here on Earth because of the difference in atmospheric pressure. And I forget the RPM we're at. I think it's 2,800. I don't know why that number is ingrained in my head, but I think it's 2,800 RPM. So they're flying pretty fast. But if you were to use those loads here on Earth and you were to fly it in Earth atmosphere, they would instantly shatter. So they've been optimized to fly on Mars. How is it going to be released on Mars? Fun question. You can think of it almost like the rover's going to give birth to the helicopter. Currently, the way it's mounted, it's underneath in the belly panel. So literally on the bottom part of the rover here, it has kind of like a shell that once we're on the surface of Mars, the first thing we have to do is release that shell, move forward, release the helicopter, deploy it. Then the rover has to move away, and ultimately then the helicopter gets to fly. How expensive will it be? The whole mission is $2 billion. That's the short answer there. What energy does the drone use? It actually has its own solar panel that charges up the batteries. So again, the trade-off is now how do you design and optimize that battery to fly for the up to 90 seconds as we've determined we need, while also keeping the electronics and the heater on overnight so that the battery doesn't freeze. It's the kind of trade-offs we have to design and optimize around. So it's very challenging. And the cool thing about the helicopter is that it's mostly built from commercially off-the-shelf parts, which is a first. So there are many implications to that, and we'll cross that bridge once we succeed in this flight, hopefully. We currently use nuclear energy on the rovers. The rovers have thermonuclear power generation. RTGs, radioisotope thermal generators. They use this thing called joule heating, which if you all take mechanical, if you decide to go down the mechanical engineering path, you'll learn all about that in heat transfer and how we can use heat and specific sensors to generate electricity. And that's basically what we do here. It's relatively non-fancy, but obviously there's some Department of Energy secrets stored in there. Nuclear power on the helicopter. Look up the Titan vehicle, the Dragonfly vehicle that we're going to fly in Titan in a few years from now. That should answer your question. But cool, guys. I do have to get going.
All right.
So thank you all once again for listening to me blabber on for an hour. Hopefully you guys learned a few things, and if anything, right, surround yourself by awesome people. Keep working hard. Keep doing what you do. You guys are all awesome. Keep it up. And thank all the teachers and the mentors you guys have, because they're doing an awesome job.
Thanks so much for the valuable advice there.
Thank you very much. Really appreciate it.
Okay. Thank you, Elio.